So welcome everyone. Thank you for joining us today for the first pre-summit webinar series. This one will feature the Water Isotopes Working Group with co-chairs Adriana Bailey, Kim Cobb, and David Noone. So we're very happy to have you guys on here, and thank you so much, David, for offering to present. I know for those who aren't aware, he's on the other side of the globe, so early morning for him. So thank you so much. I will just let you take it away, David.
Yeah, great. Thanks, Jenny. I just want to sort of emphasize that I'm quite pleased that Kim and Adriana are able to join us all today as well. So all three of the co-chairs here are available for questions and for some of the discussion. One of the nice things about being on the other side of the planet is I can give you a preview of tomorrow. So far, it's a little bit rainy, but we are expecting some sunshine. So hopefully that's going to come around to you guys as well. I wanted to spend the time on the our summary here, as in some ways reflecting on not only the accomplishments of the last year or so as sort of the progresses of our working group, but also in the spirit of the way in which even in the last couple of years, I would say the last 3 years, there continues to be a major transformation in the ability to use isotopic information to understand the climate system, both from a process level, but also from a synthesis level. And that synthesis I take as a code for thinking about climate variability on multiple scales, from minutes, the process scale, the synoptic scale, thinking about weather forecasting paradigms, as well as decadal variability, and indeed longer into centennial and even millennial timescale variability. There's been quite major accomplishments. In some ways, this is driven a little bit by our tooling. I will come in the very next slide to a synthesis statement, which comes out of some of the working group reporting that we've done. That's really this transformation from thinking about our tools, which perhaps is where we were 10 years ago, maybe 5 years ago, to really thinking about the transition from tooling to the science deliverables, which is where we're up to at the moment. So just really a very brief summary of what I wanted to cover on behalf of the group here. Two major activities that have gone on over the last couple of years have been two major field programs, the Atomic and Eureka programs, Atomic being the US supported component, Eureka being the European component of a major activity in the tropical Atlantic, looking at the trade wind area near Barbados, and Mosaic being, again, an integrated international program in and around the Arctic. And this is somewhat of a snapshot of the Arctic in and around the formation of sea ice, but sort of a snapshot of the function of the Arctic at this time relative, at this time, which will be a great contrast point to future syntheses, and also the Sheba effort that was done about 25 years ago or so now, perhaps being the previous one. Also, there's also been major investments in observational work, and I mentioned a couple of field campaigns there, NASA efforts as well as NSF efforts, and these continue. I will come back to talk about this need for routine observations, which is a major theme for our working group, both remote sense efforts, but also surface-based, whether these be seawater collection, rainwater collection, or routine water vapor measurements. That comes up towards the end. Another highlight, I wanted to make sure that we mention this important work that we have here as the US CLIVAR groups, plural, and for us, in particular, working with our European and international partners, really trying to maintain community, particularly early career scientist community, during these unusual years that we have. We are missing our in-person opportunities. So really thinking about what we can do by virtual workshops and other sorts of engagement activities. We had a highlight earlier last year, towards the end of last year, with an international meeting. So I wanted to mention that as well. So this notion of advancing from tools to science, I wanted to actually reflect. I took this slide from actually the presentation or update last year with a few modifications here to capture the latest. And in some ways, this notion of where we're going and where we've come from, we have functionally the same words, but they become increasingly refined, and that very much characterizes both our observational, our modeling, and our scientific theoretical thinking here. So one of the key areas that we have that brings us together as a community is our common research tooling, observations and models being part of that. And so part of the synthesis work that the group has been able to oversee continues to be advocating for this notion of essential climate variables and thinking about the isotope ratios of seawater, rainwater, or water vapor really as essential climate variables that need to be monitored. Thinking about the hydrologic response to climate forcing, the isotope ratios are really a way to understand the mechanisms responsible for those hydrologic responses to climate change and the other sorts of environmental change as well. Fundamentally, we still lack the coordinated and federated databases and measurement programs to enable that reference climate databases to be established, or reference climate information to be established. Of course, there is substantial progress in various small areas, but still that coordinated effort needs work. There's been a lot of work in the last few years in improving the ability to make measurements of isotope ratios from aircraft. I view this as a paradigm shift in the sort of science that can be done. Previously, this type of information was not routinely available, only a few snapshots, case studies. That's still the case. Campaigns are always campaigns, but greater integration with other efforts, and two I've already mentioned. Similarly, remote sensing has had major expanse. There's now operational algorithms running both from European, US, and Japanese platforms, really putting isotope measurements, the HDO molecule particularly, into that operational phase. And I'll mention a particular application of that associated with weather forecast and improvements of operational weather forecast skill because of that operational investment. And within the NOAA paradigm, I think about JPSS and the CRIS instrument, particularly a high resolution cross-track scanner. Let's see. We still have major investments in the terrestrial ecosystems through the NEON network, principally, the NSF-supported NEON activity. But also there's been a scientific recognition of the importance of these gold or high resolution sites or highly instrumented sites, particularly for some of the applications to process studies where it's actually insufficient to have just the isotopic information. It needs to be paired with other types of state-of-the-art measurements. And so thinking about tropical processes, marine processes, as well as terrestrial processes, these gold sites, these major investment locations have a great deal of scientific benefit to complement wider, lower investment or lower tech investments in broader observation. So there's a nice complementary field there. Sort of the parallel here, I wanted to mention some of the modeling work. I think in some ways modeling has two components, like observations do also. There's a tooling aspect. These are the tools we use to test our hypotheses, but they also represent our understanding of Earth's behavior, the way the Earth works. And so in that sense, improving our modeling is actually a statement that we've improved our understanding of the way the world works. So there has been quite a lot of advance in thinking about the way in which isotope ratios identify shortcomings in existing boundary layer, shallow convection, and deep convective parameterizations within the models that have been tested. These are CMIP class models. This sort of work has really relied on these observational data sets which have become available. Aircraft measurements, routine spatial sampling, as well as investigator-led process studies. And again, developing that theory then feeds into the modeling tools that are required to exploit the value of those observations. So a number of the major modeling centers have had investments in isotope ratios within their code bases. There's an emerging need and interest in delivering intercomparison project to the wider community. So an isotopically enabled parallel to some of the CMIP style intercomparisons. There are some specific experiments that come there that are distinctive for the isotopic measurements. But also beyond sort of the global CMIP class models, a hierarchy of models from simple box models, profile, multi-box, cloud resolved models, as well as cloud resolved models and LES models have all had a great deal of maturity over the last several years, particularly over the last year or two. And so there's a major shift in the types of tools that are available that really does represent that new science that's required to develop that type of tooling. To get information out of the proxy archives most reliably, understanding the way in which those proxy records have been deposited is essential. Many of those processes can be modeled with a great deal of fidelity. Others can be modeled with less fidelity, but the uncertainties can now be better understood through the higher resolution data. And again, this is where those gold sites becomes really quite essential to understand those properties of those that deposition process. So this is the proxy system models that enable direct modeling of the proxy records themselves. A gateway is provided by those types of models into thinking about data assimilation on a long time scale. This has been mentioned in our last year's reports. Think about how we do assimilation of proxy records to understand climate variability. Okay, I wanted to mention a couple of highlights. The Eureka Atomic Field Campaign was undertaken. The field component was actually at the beginning of 2020, with the remainder of 2020 wrangling data. And in the last year, we've seen some of the synthesis data products emerging and some of the science products starting to emerge. I wanted to mention a few things, both logistics, what was actually done here. There was a major investment in research platforms, actually indicated on the right-hand side here, a map of the experimental domain, where we see the coast of South America here, the Leeward Islands, and Barbados is in the middle here, which was the base for the experiment. You can see the major assets that deployed for principal ships, plus some others, 2 research aircraft, the ATR from Europe and the NOAA P3, one of the NOAA P3s, as well as a variety of ocean-based and air-based drones were deployed for process-oriented studies as well. So you can see this is a major sampling network that was undertaken for about a month intensive, 2 months slightly less intensive. Some of the objectives were ones that were really quite essential to understand the mechanisms of this region. Cloud organization being the key, really the exchange between the ocean surface, the marine boundary layer, into the subcloud layer, and the formation of organizational structure within the clouds being a focus point of Eureka and Atomic across the board. The degree to which cloud systems, particularly cold pools, can enhance the exchange of the ocean surface to act as a feedback mechanism in the hydrologic and energetics of these systems. The isotope ratios are quite useful in characterizing that, because they can identify the specific fluxes and give rise to this understanding of the coupling between the different water cycles. Alongside the observational component, there was a major effort that is now spinning up in modeling and also implementing or integrating the remote sensing. I just note here that one of the synthesis data papers is now in review. It's actually a 2022 paper from which this figure arises, and actually led by one of our group co-chairs as well, Adriana Bailey there, led this particular paper. An example of the data sets that come out here is illustrated on the right-hand side from the aircraft profiles, which were made from 2 aircraft on similar points in the flights on 2 days. The measurements themselves were made by placing instruments on board the aircraft, with pulling air samples in from outside. There's some always with these sorts of measurements, some technical details which make this work neatly, and that's associated with some of the inlets and the operation of the instrumentation. What's impressive about the figure on the right-hand side is, first of all, the 2 aircraft make measurements which are very similar to one another in the broader sense. So we have some confidence in the cross-calibration between these 2 aircraft platforms, which are operated effectively independently with slightly different mission parameters, but where we have overlaps, they overlap well. What we also notice here is there is a lot of heterogeneity between individual vertical profiles. If we look at the collection of the greens and the collections of the yellows from the 2 aircraft, each individual aircraft is making quite a degree of heterogeneous measurements. This is true natural variability, but also the different specific regions that the aircraft are making the measurements is again quite different. These differences are important. They represent some degree of the signal that is there now for interpretation. This is capturing, for instance, the heterogeneity within convective detrainment regions in the cloud layer and the more homogeneous, well-mixed subcloud boundary layer below. So this type of information is bringing the isotopic platforms that we have up to the scale that we expect from state-of-the-art research programs. To support those types of measurements, an example in the updating of theoretical understanding and the way in which we interpret these measurements, I view also as a highlight, a paper by one of our international members of the working group, Camille Rizzi here, has been illustrating how theoretical understanding of the cloud systems allow the isotope measurements to be used to help inform the processes which are captured within the processes within the convection and the boundary layer processes that are underlying those distributions. So what I'm really getting at there is this two-way street, that this notion of tooling and science is really saying in some ways that the isotope ratios are simply a tool to understand the science. We can refine our tools, and here's an example of how we do that refinement. With those refined tools, the observations can then be used to get at our underlying science questions. So there is that two-way street. What is being shown here is this idealized version of tropical convective clouds where we have entrainment and detrainment, relatively shallow clouds, interaction with the larger scale regional subsidence and dry air, as well as some of the microphysical processes. We know cloud droplet evaporation gives rise to cold pool generation. Upper tropospheric detrainment is critically important for the formation of upper atmosphere clouds, and water in the upper atmosphere being particularly important for some of the water vapor feedbacks, but also the role of rain evaporation in remoistening the lower boundary layer. So without going into too much detail, I want to illustrate on the right-hand side the variation in the delta D profiles resulting from various assumptions are quite distinct for both the vapor and under different entrainment phases for both shallow and deep convection. The magnitude of the signals here we can imagine in the context of the observations that are required. Of course, these types of simple modeling and theoretical understanding of these sorts of processes give rise to nice smooth profiles, of course. But when we look at the observations, we have an inherent stochastic behavior of the true atmosphere. So a combination of the stochastic drivers of these simple process-oriented models gives rise to the understanding of the behavior of the humidity. Another example I wanted to highlight, and this actually comes from the Isotope workshop that was led from Bergen and European partners, is an example in weather forecasting. Kei Yoshimura's group has been working with data assimilation of isotope ratio information for several years, and in the last couple of years this has come to maturity with several papers, one here from GRL, but also a couple of others have come up in Science Advances and other places, really leading this charge. I will note some heritage here back to CLIVAR, that some of this work started with Kei Yoshimura when he was at Scripps working within the GWEX and CLIVAR framework, working with the GFS forecast model and embedding isotope ratios into the GFS model, so GSM. So this is an assimilation of operational HDO satellite data into GSM, and what the figure illustrates, to my mind, again, this is another remarkable result, showing the improvement in forecast skill relative to a simulation or an assimilation where they've not included the isotopic information for a number of parameters. So what we're looking at here on the x-axis for several parameters is the lead time for a series of forecasts, and the experiments that are being done here is in green, where the assimilation has been, the assimilation is using just the water vapor content from IASI, which has some similar characteristics to the CRIS instruments, a thermal infrared instrument, versus an experiment where only the isotope delta D is assimilated, and then the purple is where they've both been assimilated. So the both there is where there's the value added. What do you get extra from the HDO that you cannot get from water vapor alone. And we see for HDO, actually remarkably, you can assimilate HDO, so you can generate these products. Both ends up being particularly useful. Perhaps that's no surprise. And in fact, arguably, that's a demonstration that the system itself works. Where the great advantages come is when thinking about even very basic quantities like temperature, geopotential height, and precipitation, but also the wind directions, the magnitude of the wind speed. The HDO information provides an additional constraint on these fundamental characteristics of the atmospheric circulation. One can ask, why is this so good, actually? And I think that's a really valuable question to ask. In their analysis, what they find is principally what the HDO is able to do is capture a constraint on the large-scale atmospheric transport, and particularly the vertical transport of water, whether that be resolved scale vertical transport or convective scale vertical transport linked to the coupling of the boundary layer. And so those types of transport properties are not well constrained by traditional measurements. So the HDO is adding something distinctively better, and in these experiments leading to a distinct improvement in forecast skill, which is a very different type of approach that's being taken to the isotopic information. And again, I think this is a paradigm shift in the way that we think about using isotope data, similar to the paradigm shift we've seen in the observational domain, and similar to the paradigm shift we've seen in previous years in these sessions associated with assimilation of paleoclimate data for looking at decadal, centennial, and longer timescale variations in a synthesized way, in an integrated way. Okay, I wanted to mention a little bit more on the workshops to give you a flavor. I've made a typographical over there. It's actually 150 participants, not 350, so I'll make sure I correct that. I'm sure there was 350 enthusiasts who would like to have been there, of course, but only 150 or so were able to attend. This was actually, it was a very neatly organized hybrid workshop. There was a principal hub in Bergen, which was the head office with Harold Soderman being based there. And both Harold and Camille Rizzi are members of the Isotope Working Group, some of our international partners. And the organization of that hybrid workshop, I would say one of the best COVID era workshops that I've attended, I have to admit, where the hybrid mode had regional hubs where people in certain cities were able to get together at their universities or other research organizations, as well as individual Zoom participants, and it worked remarkably well. Struggling time zones, of course, both here in New Zealand, folks in Australia and Japan, where there's a major hub, were exactly out of phase with the time zone. We're approximately 12 hours off UTC. So we had some challenges there, but overall it worked remarkably well. A few themes came out very clearly. Many of those I've already mentioned, thinking about process studies, observational data sets, refined modeling tools, as well as examples of where the isotopic information is now moving forwards into the science deliverables, which is really the core underlying value. I will note there's a great YouTube channel for those who are sick of Dave Letterman reruns. Then I recommend this YouTube channel to get you through the next COVID variant if it should arise. A couple of details from our working group itself, that we've had a synthesis paper that came out as a white paper order of a year ago, a little bit more than that actually. This has matured into a review paper, which is still undergoing some writing refinement. Many of the findings from that review paper I've already covered, so I won't go into too much additional detail now. Some numbers here. I think really we have some of these numbers are not new actually. You've seen variants of these in previous results. A couple of key outstanding details here is really this continual need for the synthesis efforts, including the types of things that we're doing here within the working group. This is still a major need to bring together the different components, and fundamentally we are still lacking this, I think of a federated coordination in a way. The working group itself is providing that within the US context. Partners in Europe are doing something similar, and of course we're working closely together, so this works quite well. It really is an essential group. The Isotope Working Group is really essential for maintaining that notion of a federated activity, which we don't have through other means. This projects onto our needs for data repositories, continuation of support for modeling tools to understand those observations, as well as maintenance of some of the remote sensing, which tends to be, in some ways, it's headed towards operational data, but tends to be very much a little bit more boutique to obtain the isotopic information out of those operational spacecraft. So some of the findings in the review paper are also oriented towards some of the science opportunities, which we've mentioned before, but I'll note a couple. Climate variability being one of those on multiple scales. I mentioned already some of those from decadal, centennial decadal, also now into the weather scales, as well as particular process studies tracking the origins of water sources, particularly over terrestrial regions. On the upper right-hand side here is an example from the Tropomi spacecraft on Sentinel-5P, and a similar instrument will be on Sentinel-5, showing remarkably global 5-kilometer resolution HDO data. And this is the type of information that's now available. You can see very clearly the terrestrial regions. Well, actually, you can only see the terrestrial regions because the data is high quality. But in the terrestrial, the land interiors, there are distinct shifts in the isotope ratios, capturing the differences in the moisture sources for the water vapor in those regions. Again, this is a theme that comes out as a science opportunity. So at that point, I will leave it there and happy to take questions. I'm sure the other members of the working group who are here would be delighted to take questions as well. Thanks, Jenny.
Thank you, David. So if you have any questions, feel free to raise your hand or you can type it into the chat box. So there is a question from Mike Patterson in the chat box. What prospects are there for US operational forecasts, including out to S2S, employing water isotopic data assimilation?
Excellent. Thanks, Mike. That's a great question, and I'll pass you $20 later on for asking the ideal question. And of course, my offer of 20 fictitious dollars applies to everybody. Yeah, the opportunities there are great. I think there's no theoretical barriers. This can be done, and it should be done. And arguably, it's a little overdue, perhaps by several years, if not a decade. The data is there. It's available in real time from both US, European assets, satellite assets. The real challenge would be thinking about the way in which the modeling tools can be brought together. So there is definitely work required to build the data assimilation system. The GSM model has isotopes. The WRF model also has isotopes at cloud resolving scale, so running WRF at 5 kilometers or better, isotopic models. That can be done. There's no limitations. There's work that needs to be done, but there's no fundamental limitations to doing that. There are one of the things I will note is that this is true for all satellite data, and there's nothing special here with the isotopes. That there's always questions about calibration and making sure biases are appropriately taken into account. We do know that there hasn't been an effort to synthesize the different satellite data sets onto a common reference and correct calibration scale. It's likely, in fact, we know there are biases that differ between them. And so a proper account of those biases is going to be essential for the data assimilation problem. But again, there's no real barrier to that. Again, that identifies the value of routine ground-based and satellite-based aircraft-based measurements to provide that validation and cross-validation between the satellites. It's a great opportunity to proceed there with data assimilation.
Just a quick follow-up then, given those threads that you just laid out really nicely, I think that encapsulate both the observational and data needs, the collaborative activities in modeling and bringing observations to bear on the models, both in situ and satellite, bringing that together. Do you see this as the potential focus then for the balance of the working group in the next year to really try to, can you describe the work of the working group that you have planned that will tackle these things specifically?
Yes. Yeah, I think one of the things we're working on in the context of the white paper, the review paper, is really effectively laying out the case for some of the major advances that can be made. And this is an area where one of those major advances comes out. So it's the work that's going to be done within the working group is really in the spirit of making the case for this is the type of work that can be done and should be done. And arguably that these are the value of these types of synthesis activities that are out there. At the moment, we haven't specifically focused on this question of data assimilation in an operational mode. In part, that the amount of work that's being done is really coming out of the group at University of Tokyo as really the leader there. We don't have counterparts at other operational centers doing this work. So their work that's starting to come out, it's been on the way for a number of years. So we've seen bits and pieces through workshops and other things, but it's really come to this mature point. I think within that notion of what can we do as a working group here, we can summarize and identify some of the value that they have identified. We don't yet have that international magnitude that says, yeah, we're well and truly overdue for this. So the case that we made for this data assimilation from an operational standpoint, I think it is that case that can be made. We don't really have that major demonstration at the moment.
One more point I'd like to make about that is that the interagency group, both within US CLIVAR, but this larger effort across agencies involving the federal coordination for meteorological services, has in its sights has placed a priority on precipitation predictability in particular. And so I was focusing in here on the forecasting capability and that Japanese effort that you talked about, that perhaps this is something for us to think about within our program, how we can help motivate a future activity in the United States that could bring this to an operational capability that hasn't yet really been a focus to help address this priority on precipitation prediction.
Yes, thanks, Mike. Yeah, absolutely. I think sort of along those lines, that notion of interagency connection is really essential. That 3 of the major agencies, NOAA, NASA, and NSF, would be required to do this well, mainly because this is sort of where the expertise and assets reside. That even through the JPSS mission and the use of the CRIS instrument, sitting on a NOAA platform, but the retrievals and the data is being generated through JPL, through NASA. So already there's a deep integration that's required there. A lot of the modeling tools and the modeling expertise on the isotopic physics, that the linkage between the isotopic measurements and the underlying processes, that sort of resides within an NSF sphere, that it's sort of the research sphere, but it's ready to transition to that operational mode. And so again, that integration of sort of an NSF perspective and moving that across to an operational perspective is exactly the way the interagency partnerships should be developed to really get those things working together. I think this is sort of a personal note. I actually think this is a great opportunity where we could actually see a major shift in the ability to make better precipitation forecasts in particular, but more generally things that are connected to making good precipitation forecasts, including the hydrologic balance of the boundary layer, large-scale water vapor transports. These are not inherently the details of what makes good precipitation forecasts, but they're the things that are around good precipitation forecasts. You need to do those things right as well before the precipitation results is good results. So yeah, I think that's an important point.
I just wanted to chime in on another reflection on the work going forward and the groundwork that we've laid, which is in the area of just following up on the threads in the observational space in terms of large networks of observational platforms that are being actively designed. Of course, David mentioned TPOS 2020, but I believe it was really at that CLIVAR sponsored workshop where I think it was a tropical linkages basins workshop. I may be butchering it, but really so heartened to see the impact of our working group in terms of helping the community at large to understand, in part through our presence there, but in part through raising awareness about the capacity to really accelerate work across the ocean atmosphere community in general. When we can leverage these kinds of observations. So seeing those rise up on the priority list again and again from the different subgroups, be it focused on synoptic scale, up to and including, integration of paleo scales was really, I think, rewarding, and certainly threads that we will not let fray in our hands going forward. We will be chasing down those opportunities and staying actively a part of those communities, and seeing if we can follow through on establishing water isotopes in whatever phase we want to see them become a more commonplace part of large observational networks at that kind of basin to global scale.
Great. Thank you, Mike. Thank you, Kim. Any other final questions for the co-chairs? Right. So I don't see anything in the audience, and I see we're 8 minutes over, so I think we can end here. So thank you again, David, Kim, and Adriana, for tuning in and giving us the presentation update on the Water Isotopes Working Group. And thank you everyone else for participating. Have a great day.